If you were, because we can type these in our calculator, maybe I'll show you how to do that if we have time here at the end. If you were to go to your table, any of these points, so what? We got -4. So anything in that little range right there. So just to the left of -4 and up to -6. All those values would be undefined. Okay? Because to be defined, it just means that when you plug x in, you get an output, right? If I plug in, if I think about -5, -5 is not in there, right? -5 is not in that range or interval, and -5 does not belong inside that interval as well. So there's nowhere for me to plug -5 in to get an output back. Does that make sense, everybody? So that's a very good question, Chris. When we do these, you're going to, you can have 2 pieces, you have 3 pieces, you have 4 pieces, but the logic, the concept is, if you can do 2, then to do 3, just do 1 more, right? Just do 1 more graph, okay? If you want to do 4, just do 1 more graph, okay? They can't get complicated, they can't get ugly, but that's the general process behind piecewise functions. There is a function that I want you guys to learn, and it's kind of a piecewise function. We don't necessarily see it in notation-wise as a piecewise function. There's actually 2 functions I want to talk about real quick, I guess. You know a piecewise function. You know that the absolute value function is a piecewise function. Because the absolute value function says that you graph x if x is greater than or equal to 0. And you graph the opposite of x if x is less than 0. So you've dealt with piecewise functions before. Probably not in this manner. You never saw the word or the phrase. But when you graph an absolute value function that's linear, you're doing a piecewise function. Because if I do, get this open real quick. It's a lot easier to graph piecewise technology-wise with GeoGebra than it is to use your TI-83 or 84. But if I just type in x, okay, and then I write if, I think I gotta write, maybe I don't have to write if. I'm just gonna write 0 is less than x is less than, or 0 is less than x, gives me the whole thing. Okay. Come on. There we go. And you see here then that that function was defined using that rule, and you're using interval notation here based, or I guess that's not a rule. I don't know why they put it in parentheses, but whatever. But that gives you the right hand side of the absolute value function, right? But if I now say that I'm looking at -x for x being less than 0, it gives me that. And is that function there, if I graph the absolute value of x over top of it, the blue one's the same thing, right? So your absolute value function is defined in a textbook. Every textbook you see that talk about absolute value, they will, in the notes of that textbook, somewhere show you that the absolute value is really this thing. Okay? It's positive x when x is greater than or equal to 0. It's the opposite of x if x is less than 0. Now, GeoGebra wasn't able to do the equality part, but visually you didn't see that issue. Another function that I want to talk about is the greatest integer function. Greatest integer function. It looks like this. This is the notation we use for it. F of x equals, and a weird bracket there. And they put the expression, it says, right now I'm just going to deal with x. And they got that other weird bracket there. Okay? Sometimes you might see it, I've seen it in other textbooks as just that. Okay? I've seen it in other textbooks as scope. Kind of like that. Okay? This is a little bit different because this is what we refer to as a floor function here on the bottom. And sometimes you may even see it written this way. Okay, if that's a floor function, what do you think that's called? Ceiling function. Okay. And we'll talk about, I think maybe once we talk about the greatest integer function, you might understand why sometimes it's called a floor function. Okay? But what the greatest integer function says, no matter what your x value is, you are going to take it and round it down to the last greatest integer. Okay? The last greatest integer. And that's going to give you then an output value. Okay? And that output value is obviously going to be your f of x. But what this means is, if I have f of x equals 2.5, I'm going to round down to the last greatest integer. So what's the last greatest integer? 2. Okay? So I have then the ordered pair, x was 2.5, y is 2. What if I have f of x is equal to the greatest integer function of 2.9? What's that going to round down to? 2. So now I have 2.9 comma 2. What if I had the greatest integer function of 2.9999? What's that going to round down to? 2. Oh. 2.999992. Okay? So because I'm getting the same y values back there for any number, any x value that's between 2 and 2.999999999, it gives back a y value of 2, right? Hopefully if you visualize that, what kind of line segments is that going to provide you? If all the y values are 2. Horizontal, right? Okay. So I give you a small horizontal line segment. Okay. What is kind of something we got to pay attention to if I say f of x is 2? Okay. We don't round back down beyond that. Okay. So if you have a whole number, an integer, then your result is that integer. Okay. So the greatest integer function evaluated at 2 is 2. So you get the point then, 2 comma 2. Okay. Now, kind of give you a situation that you guys are impacted by in regards to the greatest integer function. Do you guys have data plans for your phones? Okay. So if you got a data plan for your phone, say you have like 8 gigabytes. Okay, if I have 8 gigabytes, let's say that costs me, let's just make it easy, $100. Okay, that costs me $100 a month for 8 gigabytes. What happens when I get to 8.0000001 gigabytes? You're now paying $110 or something, right? They give you that surcharge of $10. Okay? Now, no matter how much of that 9 gigabyte I use, if I go 8.5 gigabytes, am I still paying $110? Okay. So there's some function that takes that 8.5 inside Verizon. It's taking that 8.5 that they're receiving from your data usage, and it's applying your contract rate and all that kind of stuff, and basically saying they're into their 9th gigabyte, so attach $10 to that. Okay. No matter how far they're into that 9th gigabyte. So if you get 8.7 gigabytes, you still get that one additional fee at $10, right? If I go 8.9999 gigabytes, I'm still paying $110, right? What that's called is it's a greatest integer function. Now, their programming and stuff like that is all attached to your contract, and there's intricacies in regards to that. That's taking the 8.7, basically saying that you're going to pay for that 9th gigabyte and attach that then to your bill. But you are impacted by what we call a step function. Okay? Because once you get into that 9th gigabyte, you go up a step. Does that make sense? And now once I get into the 10th gigabyte, I'm going to go up another step of another $10, correct? Okay? Kind of graphing what just a general step function looks like, the greatest integer function. And actually, let me do it this way. Let's get to this thing. Just kind of make graphing a little bit easier if you got these grids. Alright, so what happens if I have, let's just do f of x equals the greatest integer function of just x. Okay? So what you would see at Verizon or whatever, or maybe if you make long distance phone calls or you call like a psychic hotline or something like that where it says it's $1.99 for the first 10 minutes, but it's $4 for every minute after that. Those are step functions, those are greatest integer functions. So they might, whatever's in the, whatever the, what's the word I'm looking for? The expression, whatever that expression is, can change, okay? But we plug in x, evaluate with that expression, and then realize, okay, what's my output now? And now round it down, okay? So if I get, let's just do a couple like we said, if f of x is equal to the greatest integer of, let's just say, 0, okay? If we're at 0, what integer does that spit back? 0, okay? So, x was 0, output is 0, right? Okay, so x 0, f of x or y is 0. So I'm going to plot that point. Okay? Now, I'm going to try like f of x is equal to, 0.25 or 1/4. What's that going to go to? That's going to go to 0 as well, right? You go back down, round down to the last integer. So at an x value of 0.25, so maybe, let's just say that every one of these is, okay, so two blue grid lines are equal to 1. Okay, so that's 1, 2, 3, 4. That's going to give me, so 0.25 is going to give me the 0. So 0.25 would be about right there, right? Graph that point, 0.250. What about 0.5? It's going to get me to 0 again, right? What about 0.9999999999999999999? Keep saying it. What's that going to round me down to? 0. Now, Jackson, don't stay it. Can I get back to, can I actually graph 0.9999999999999999999999999999999999999999999? You're not going to. So what are you going to graph at?
Like a little bit before the 1.
Okay, so the best way to do that,
Open dot at the 1.
open dot at the 1. Open dot at 1 tells me, yes, just to the left of 1. Okay? And now, we have, and all these other points in between are going to fill in and give me that little line segment. Does that make sense? But once I get to 1, once I now evaluate at 1, if f of x is equal to the greatest integer function of 1, what does that round to? 1. So now the x value of 1 gives me a y value of 1. Okay, so x value of 1, y value of 1, and now I've got a closed dot. You have an open dot on top of a closed dot. Does that make sense? Is that okay for the vertical line test? Yeah, we'll pass the vertical line test. So now if I go to 1.5, I get 1. Right? Round back down. So 1.5 be 1. But if I'm at 1.999999999, it's going to be open dot at 2. Okay? And then when I get to 2, greatest integer function of 2 is going to put me at 2. Okay? And really what's really nice is once you start to get maybe 2 line segments, it's a pattern that stays consistent for the rest of the graph. So that line segment, cut and paste to there, cut and paste here, cut and paste there. Okay? And what's really nice is we can cut and paste this way. So open dot there, close there. Okay? So what's interesting here is like if I had like -0.5, -0.5, I'm going to round, I'm going to go to the left on the number line. And that's what all this stuff was doing, right? Okay? If I'm here at 0.75, I round left to 0, right? So if I'm at -0.5, I round left to -1. If I'm at, that was 1, so if I'm at -2.24, okay, I'm going to round left to -2. And we see that graph is going to continue to provide basically steps on to positive infinity and negative infinity. Does that make sense? That's why it's called a step function a lot of times. Okay. Now, it's also called a floor function. Okay, and a floor function, you might see it written this way. Oh, doing that wrong. Written that way. Because what kind of rounding do we do? Rounded down, and down is towards the floor. Okay? So if I was going to round up, which could be a potential need, okay, what would I call that? A ceiling function. Okay? We're going to deal right now, unless told otherwise, always assume that it's a floor function, or when they say greatest integer function, you're rounding down until they tell you otherwise. Okay? But there may be some application where it makes sense to round up. Okay? The rest of the PowerPoint just kind of talks about things that we've mentioned already, such as the vertical line test. Okay? What I want you guys to understand is, if we look at this vertical line test phrase here, okay, this is a curve in the coordinate plane is the graph of a function if and only if no vertical line intersects the curve more than once, which is essentially what I've got written over there on the board, right? On the whiteboard. I'll enlarge this so you can see it on the camera. But do you remember what the phrase "if and only if" meant from geometry? I'm talking to my geometry students right now about it, and they're kind of struggling with what that phrase means. It's a notation. It's a specific phrase that tells us how we can read that. Okay? And what it means is, if your graph is a function, then it passes the vertical line test. Does that make sense? But you can read it backwards and say, if you pass the vertical line test, then your thing is a function. Okay? So it's a two-way street. You can read it left to right and right to left. If you pass the vertical line test, you're a function. Or if you are a function, you pass the vertical line test. That's what the phrase "if and only if" means. It's a very important piece of notation.
We're looking for a student that drives a blue Jeep that is parked in the gym parking lot. If you would please come to the office. Thank you.
It's a very important piece of information as you move into more advanced math classes. When they ask you to start proving things, you would actually have to prove that twice. You'd have to prove both directions. Does that kind of make sense? And it's a concept that people want to use all the time in every phrase that they see. It's nice to be able to reverse things mathematically. Okay? We hear the phrase, if it's a square, then it's a rectangle, right? But then people want to reverse it and say, if it's a rectangle, then it's a square. Can I do that? No. So that phrase is not a biconditional. So we would never say it's a rectangle if and only if it's a square. Okay? Because you can't reverse it. We would say, if it's a square, then it's a rectangle. And that's the only way we can imply that and interpret that truth. Okay? Here, there are two truths written inside that statement. Okay? So that's important to think about. Make sure you're comfortable with the vertical line test. Some of your questions, your homework, are going to just be a picture and say, does it pass the vertical line test, that kind of stuff. There's a website assignment. I think I got it open until Tuesday. Start working on that. You can ask questions on Monday about it. That's all I've got for you today.